All right, so now we are done with the algebra and trig review, and we can finally start the content for this course. So chapter 1 deals with limits. We're going to be covering sections 1.2 through 1.5 in the textbook. And recall that the topics in this course sort of three main categories. You can break it up is limits is the first one. Second thing is derivatives. And the third thing is integration. So limits, this is chapter 1. Derivatives is chapters 2 and 3. And then integrations chapter 4. All right, so these are the three main topics for this course. And finally, we are now starting the first topic, which is dealing with limits. Everything's going to rely, like derivatives and integration are going to rely on our fundamental understanding of limits. All right, so section 1.2, this gives the introduction into what limits are and how to estimate limits using graphical and numerical approach. And I think it's best just to demonstrate an example. And in this example, let's say I consider the function f of x equal to x cubed minus 1 over x minus 1. And the goal is we wish to find what is the limit of f of x as x approaches 1, whatever that means. And what I went ahead is I drew a rough sketch of the graph. So what you see in green is the actual function, graph of the function, and I used blue for the coordinate or the axes, x and y axes. And if you notice that at 1, there's this hole. So at x equals 1, there's a hole in the graph. And that kind of intuitively, it sort of makes sense why there would be a hole. So essentially we're saying that the point, usually that'd be 1, 3, doesn't exist. And algebraically, if you plugged in 1 into the function, so like f of 1, that's equal to 1 cubed minus 1 over 1 minus 1, and you get something that's of the form 0 divided by 0. All right, so, and this is called a sort of indeterminate form because you can't divide 0 by 0. So you can't do 0 divided by 0. We don't have a true definition for what that is. All right, even though there's a hole on the graph at 1, so I'll sort of summarize this in a different color. So even though there's a hole, the limit still exists. And why this is because the limit sort of is a description of the behavior of the graph. So this is a description of the behavior of the graph as the x coordinates, as the x values get, and I'm just going to use quotes, really close to some particular x values, some particular sort of static x value that's fixed. So get infinitely close to some fixed value. And in this case, we're wanting to know what's the behavior of the graph as its x values, as the x coordinates of the graph. So as the x values get really close to the fixed value 1. That's what we're going to, what we want to know. So before I move on and keep going with this, I drew the graph of the function in green, and you'll see that there's a hole at the point 1, 3. That means there's no point. The point does not exist on the graph. And when you can also algebraically determine that, just because if you plug in 1 in for x, you get 1 cubed minus 1 over 1 minus 1, which gives you 0 divided by 0. But 0 divided by 0 is indeterminate. So there's a hole in the graph at that point 1, 3, which means it doesn't exist. But even though there's a hole, the limit still exists. So the question is, what do I mean by limit? Since how can this limit still exist, but there's a hole in the graph? And all a limit is a description of the behavior of the graph as the x values get really close to some fixed value. So in this case, we want to know what's the behavior of the graph as the x values get really close to the fixed value 1. And I'll just redraw it again. So and like we said, there's that hole in the graph at 1, 3. So as we get really close to 1, so as x gets really close to 1 from the right side, so we're getting really close to 1 from the right side, the y coordinates that correspond to these x values are getting really close to that hole. and that y value of that whole is 1, 3. So I'll go ahead and write that. So we say as x gets really close to 1 from the right side, the y values get really close to 3. So the y values get really close to 3. Now, if we approach 1 from the left side, so let me use, let's see, I'll use yellow. So if we're getting closer and closer to 1 from the left side, the y coordinates of these corresponding points are also getting closer to that same y value of 3. All right, so as x gets really close to 1 from the left side, the y values of the graph get really close to 3. So say closer and closer to 3. All right, so what I've just written is a description of what the graph's doing. So this is our description. So I'm going to say description of what the graph's behavior is. As we get closer to the particular value, fixed value of 1. And so we would say the limit based on this behavior we would say, let's say, quote, the limit of f of x as x approaches 1 is the value 3. Again, this is just a description of the behavior of the graph as the graph gets closer and closer to some fixed value. So even though we know there's a hole at the point 1, 3, we know that as x gets closer and closer to 1 from the right, so that's the red arrows pointing towards 1 from the right side, the y coordinates, that the red arrows again, they're pointing closer and closer to that hole. And same thing for yellow. If you're going from the left side, the yellow arrows are getting closer and closer to the hole. And the hole has a y coordinate of 3. So even though there's a hole, it's still a limit. Just the limit is the description. It is saying the graph gets, as x gets closer to 1, the limit is going to be 3. Notationally, so I call it limit notation. I might write the following as x, and then I have an arrow for approaches 1, f of x, and then I have another arrow approaches 3. So the arrow is going to be approaches. That's one way I'm going to write it. And the other way, for the notation, they might have LIM for limit, and then as it's underneath that in small text, they'll have X with that same arrow going to 1, and they'll say f of X, but then that will be equal to 3. So the equal sign just means what the limit is. And so the limit is 3. As X gets closer to 1, the graph gets closer to 3. All right, so in general, I might write it as X approaches some value C, f of X approaches some value L. And so C and L are just some numbers. Or it'll be limit LIM, X approaches C, and then f of X equals L. All right, so what I've done here is determine the limit from its graph. This is using the graphical approach. So what we just did is used the graphical approach determine the limit. And so our function was x cubed minus 1 over x minus 1. So from the graphical approach, we would say limit as x goes to 1 of x cubed minus 1 over x minus 1 equals 3. That's how we would write it in a condensed format. And the crucial thing to know is that even though there's a hole, the limit still exists. Right, and again, a limit is a description of the behavior of the graph or behavior of the function. All right, and I'm going to keep going with this same function, same limit, but we know from the graphical approach, we got it to be 3 for the limit. Now the numerical approach is just another way of getting to the answer, so numerical approach. You just make a table, and one of them's x and then f of x, and then you plug in values into the function and just see what the y coordinates are after you plug it in. So I would pick values that are close to 1. Let's say I did 0.99, that's one of them. And just to demonstrate, if we plugged in 0.99, and our function's x cubed minus 1 over x minus 1. So that's going to be 0.99 cubed minus 0.99 minus 1. And if you were to put all that in the calculator and sort of round, This comes out to be 2.970 rounded. So I'm just going to round to 3 decimal places. All right, so plugged in 0.99, the output 0.2970. All right, and it might help to pick some more values to plug in to get a better feel for the graph. Now let's say I did 0.999 with 3 nines. If you plug that in, you get its Y value corresponding output to be 2.997. All right, and right now if I plugged in 1, we don't really know what that's going to be because that gave us an indeterminate form. Now these two values are values that are to the left of 1. So I might want to pick some values that are to the right of 1. And let's say I picked 1.001. So that's some value really close to 1 from the right side. You'll get this to be 3.003. Likewise, if I did another one, if it was 1.01, you get this to be 3.030. All right, and this table is just a summary of the values you get plugging them into the function and getting the corresponding outputs or Y coordinates. All right, so as the values, so these are X values getting closer to 1 from the left. Left side, you'll notice the Y coordinates are getting closer and closer to what we can estimate to be 3. Likewise, so if we go from the right side, all right, getting closer and closer to 1 from the right side, you get the Y coordinates that are also getting closer to 3. Therefore, so we conclude by the numerical approach limit x goes to 1, x cubed minus 1 over x minus 1 equals 3. All right, so same conclusion, just instead of graphing, we're plugging x values into the function that are really close to 1 from the left side and right side, and their corresponding y values are getting closer and closer to 3. Now it's getting closer and closer to 3, and it looks, I'm approximating it, all right? So I'm estimating that it's gonna be 3, all right? Just based on the behavior, as I did 0.999, that was 2.997, and then 1.001 was 3.003. All right, the point is that this was an estimate. I'm estimating the limit. Same thing with the graphical approach. So I'm going to make a comment. The graphical approach, because I'm sort of just observing it, and based on how the graph is drawn, I can visually tell that it appears to be getting closer to 3. So the graphical approach and numerical approach are approximation methods or estimating methods, or estimate. All right, so they're not foolproof, I guess is what I'm saying. They're not exact. So we'll learn after this section to be more exact, or to be exact. We will almost always use what's called the numerical, or sorry, use what's called the analytical approach. So called the analytical. So this is what we'll be using 90% of the time. If we can't determine the limit from the analytical approach, which I haven't done yet, then you would use these other two methods. The graphical approach probably the one I would try to do if I couldn't figure it out analytically. So the analytical approach is actually the next section, but I'm going to go ahead and just demonstrate it for this particular example I've been doing. So we had f of x equals x cubed minus 1 over x minus 1. And we want the limit, oh, sorry, x goes to 1 of this function. All right. And I'm going to do this using analytical approach. And we know what the answer is. It's going to be 3. So first, just try plugging in whatever fixed value that the x values are approaching. All right, that's usually what I try first. It's just plugging in 1, which we know that gave us 0 over 0, right? Because we had 1 cubed minus 1, which is 0, and then 1 minus 1, which is 0. All right, this doesn't tell us anything. That's indeterminate. So I'm saying this didn't help. However, from algebra, there's a factoring formula. And that factoring formula I'm going to apply is called difference of cubes. And that's a cubed minus b cubed factors into a minus b times a squared plus ab plus b squared. So that's the formula I'm going to use. So for x cubed minus 1, right, because 1 cubes 1, so I can apply this. This turns into x minus 1 times x squared plus x plus 1. All right, so using this formula, I can do the problem now. I'm going to say that's the limit. X goes to 1. Now replace x cubed minus 1 with x minus 1 times x squared plus x plus 1. All of that's divided by x minus 1. And you'll see that the x minus 1s are common factors that I can divide out. So that's going to be equal to x goes to 1, and I'm left with the x squared plus x plus 1. And now try plugging in 1. All right, so if I plug in 1, that's going to be equal to 1 squared plus 1 plus 1, which that comes out to be 3. All right, so that came out to be the same thing that we were doing in the graphical numerical approach. This is the exact way to do the more exact way to do the problem. And this is what we'll be doing most of the time, is using this analytical approach. So I figured I'll show the 3 different approaches. The first section deals with graphical and numerical approaches. The next section after this deals more with this analytical approach, but I wanted to go ahead and give a preview of what the next section is going to be. All right, and you really just try plugging in 1 at first. You got it to be 0 over 0. This doesn't help. So then I try to see something in my toolbox if I can apply something else, and that's going to be the factoring formula difference of cubes. So that when I applied it, I can divide out the common factors from top and bottom. And then after I did that, now I plugged in 1, and then I got 3. So this is going to be the way that we'll be doing most of the limits. All right, so I think I'll stop the video here and do a part 2 to this. So for the next video, there's going to be a part 2 to this section 1.2. But in this time, I'm going to focus on going through a bunch of examples, focus on going through examples, applying the graphical numerical approaches. All right, and the graphical numerical approaches, right, are just, these are approximations. They're not exact. Or estimations. So I'll be doing concrete examples in the next video. Just to recap, a limit tells you the behavior description of the graph as the x values get really close to some fixed value. In this case, we were dealing with the fixed value is 1. The behavior of the graph was that the graph for the y coordinates were getting closer and closer to that hole, and that hole has a y coordinate of 3. So based on the graph, we can see, okay, well, as x gets close to 1 from the right side, x gets close to 1 on the left side, the y coordinates get closer and closer to 3. All right, so that's why we would say the limit of the function of x cubed minus 1 over x minus 1 is equal to 3. And this is how we would going to be writing it. The numerical approach is the same kind of thing. It's just using a table of values, and you plug in values that are close to 1 from the left side and close to 1 from the right side. And then you see that these y coordinates of these that go with these x coordinates are getting closer and closer to 3. All right, so same thing, same result as 3. And that's the graphical and numerical approaches. And the main point is that these are approximations. I can keep choosing more and more x values and getting the y values to get closer and closer and closer to 3. So I went ahead and just showed the analytical approach, since this is what we'll be doing 90% of the time. And what you tried first is plugging in 1, and you get a 0 divided by 0, which is an indeterminate form. I can't conclude anything from this, but I can use factoring. And that's where the factoring canceled out the common factors, and then I plugged in 1 and I got 3. So this is the more exact way. So that way you have this example explaining what a limit is. Here are 3 different ways to get the limit. 2 of the ways have faults because they're approximations. One of the other method is going to be the more exact method that we'll be using. So the next video is going to be doing just examples first in this graphical numerical approaches.